Hello, ni hao, shalom. Welcome OpenFoamers to our next video of OpenFoam heat transfer. So in the last video we are talking about wall heat flux, and very successfully we have seen that in our post-processing we have suitable wall heat flux wall heat flux what do you call that, values that are being put out, which is great and all. Yeah, so next thing kind of want to do is to calculate the heat transfer coefficient. Now I mentioned before that OpenFoam has some sort of coefficient measuring thing available. So this is called heat transfer coefficient, so it has a function for that. Now what we want to do is to use all this data to go and construct our own function that measures the heat transfer coefficient and see what happens from there. Okay, so I want to go back, clear, and let's do an all clean on this. And let's go to system control dictionary. Okay, so what I want to do is not the wall heat flux now. I want to do a average heat transfer coefficient or heat transfer coefficient. Okay, so open and close brackets as usual, and the type, okay, it was wall heat flux previously. Now I want heat transfer coefficient, so I'm just going to copy and paste here. Okay, write this in. So next I want the libraries, which are over here. So that's pretty standard. Execute write control all this. I want that as well. So I'll just have this, and yeah, execute and write control. And next we have this thing called HTC model, which is the heat transfer coefficient model, and then they'll ask for the patches you want to calculate the heat transfer coefficient on. So HTC model, there are three kinds. One's called the Reynolds analogy. Won't look too much into that. One is called local reference temperature. So it compares the TC, I think, temperature of the said perhaps the coolant or something. Yep. Okay, so let me give that for you. So this is my thought is okay. So heat transfer coefficient is usually equals to Q over T fluid minus Ts, right? And this is the temperature of the surface. So this is a T of the wall. So this is actually the surface is the wall. Alright. I'm gonna paint all this black. But I don't want to invert it. Okay, never mind. Let me do this again. Hold on. Yeah, okay, so I'll just put it in orange. So you have this going on. So there's a T fluid minus Ts, which is the wall. Okay. So yeah, so this is the wall temperature, which is being referred to here. Okay, so or is this some kind of local temperature? Okay, whatever. So anyway, okay, so we have heat flux divided by Tc minus Tw. Tc is the temperature of the coolant, Tw is temperature of the wall, or you can use an average reference temperature, which you can key in by yourself, and that ought to be the average temperature of the wall, since that's what you want to find out. Question is, what is this Tc? Tc should be the temperature of the fluid, but what temperature does OpenFoam use? So this is the part where it gets a little more tricky, and you should be cautious with your use of this heat transfer coefficient function. So if we take a look at the C files of heat transfer coefficient, there are the models being used are the local reference temperature and the fixed reference temperature. So for the fixed reference temperature, remember we always have to define our T reference, which is in this line, I think. And what is TC then? TC is, if you take a look, we'll have this, take a look at this part where it talks about the heat transfer coefficient model. Okay, so it's going to generate a set of constants, and we take a look at this one should be pretty straightforward to you. It says the heat transfer coefficient for whichever patch I, which is the little cell you're talking about. So let's say, remember we discretize into cells, right? Many cells. Okay, so it can be of arbitrary shape. So there will be a local wall temperature here, right? And that will be sometimes used for calculation if you use the local reference temperature. Then there's a cell wall temperature. All right, this is the temperature of the cell, or this little volume element, this little block near the surface. So that will be, yeah, the TBF. Okay, so hold on. So anyway, so we have a TBF patch I and a T reference. T reference is whatever temperature you key in. And if you take a look at the difference between this and the local model, you can see that this one is TC. Okay, TC. And then we have TBF patch I. What is TBF patch I? So my guess it's the TBF here is the boundary field, temperature of the boundary field. So the boundary field should be somewhere here, right? It's at the wall, and that's the temperature of the boundary, because this is the boundary, this is the inside. Okay, TBF. Likely it is talking about this, if I'm not wrong. So TC will be the fluid temperature, as we normally look at the heat transfer coefficient. It's usually, the first temperature is usually the temperature of the surrounding fluid, and the second temperature is the temperature of the solid surface. So when we talk about this, where is it? Yes, it is TC minus TBF, and then there's an epsilon over here, which that one we just ignore for now. I think that's to deal with some turbulence and what have you with it. Hold on. So fixed reference temperature. So Q boundary field. QBF is the heat flux at the boundary field. So that's right. That's what you want. The heat flux over here. Or actually, the heat flux going from the fluid to the solid. And then TREF. TREF is something you key in. TBF patch I. That's the temperature of the boundary field at patch I. So this is this little local wall temperature here. Now that's if you use the fixed reference temperature. Now if you take a look at the local kind of a reference temperature, we will be given a TC and a TBF patch I. TBF patch I I've already explained before, and QBF patch I was already explained before. These are the temperature and the heat flux at the boundary fields. The TC here will be the internal field of whatever cell you have. So this is the local temperature. Okay, this is the TC you're talking about. Okay, so this is the T wall, and that's the TBF you find in the code. So we have to be very careful when we use this model, because if you have a local model, they're going to use the fluid temperature reference as the temperature of this cell, okay, to be the fluid temperature. Then the local temperature of the solid to be the solid temperature. All right. Now, if we were to use a reference temperature model, if you use a TREF, so that's whatever you key in, and that will usually be the fluid temperature you want to key in, some reference fluid temperature, and we'll have this local solid set temperature being used here. So this will be T solid. Alright. Now, if this TBF, this solid temperature, is the same for the whole solid, then that's perfectly alright. We shouldn't have any discrepancy between the H that we calculate manually and the H we calculate using OpenFoam. So T fluid, okay, T fluid minus TBF. So this is if the temperature is uniform between this and this, if this TBF is uniform, the boundary field temperature, that means the solid temperature field is uniform, we should not have any discrepancy. But if we have a temperature distribution across the solid surface, let's say here is hotter than here, then we will have some discrepancy if we don't use some average surface temperature. So that's something to be very mindful of when using this utility. Of course, when you use the local temperature utility, then of course the heat transfer coefficient is not going to match the average heat transfer coefficient usually found in correlations found online or in engineering textbooks. So there's something to be very mindful about when you use this utility. Just be wary of what you're actually calculating. What is TC, what is TBF? If you're confused by the documentation, the best is always go to the code and check out what they're calculating, what it looks like. So if BF means that it's the boundary field means it's the surface, and then if it's the internal field, as you can see here, internal field here, which you see for the local reference temperature thing, it is for the local internal temperature of that cell closest to the surface. So yeah, how do I know it's closest to the surface? You take a look, this patch I. So it's referring to the temperature of the patch I, where patch I is wherever you are doing your calculation, whichever cell you're doing your calculation. So if you're using QBF for patch I, that means the local, like, you know, heat flux for that patch, that little field there, and they're using this TBF for patch I, that means it's the boundary field temperature here. So I know that what they're looking for is the internal temperature in patch I, which is this box I'm drawing here, the little cell. Okay, so long and short of it, so you just got to be mindful what models you're using. So TBF patch I, so TC is the internal field temperature, the inside temperature of the cell. That's how I find is this internal field. That's what tells me it's the internal field. Is this inside temperature of this little cell of fluid here. So that's how we kind of read this code. So if my reading of the C++ code is right, then that should be what this actually means for local reference temperature and fixed reference temperature. So hopefully that clears up a lot of the confusion. I think we have some things here. Yes, this guy is it's assuming a fluid calculation with constant wall temperature. I'm going to calculate the heat transfer coefficient. Okay, so this is the this guy Eugene. Is the temperatures you use to calculate the heat flux are the wall temperature and the temperature of the first off-wall cell. So that's what I was talking about just now. So that he has the same idea, and okay, at least the code, the C++ code gives us a little bit of clue into what these temperatures are talking about. So these are all very important for calculating our heat transfer coefficient. If you're still confused, it's best still to use the wall heat flux utility, and then you kind of manually calculate the reference temperatures. I mean, calculate your own heat transfer coefficient yourself. So that will remove all the doubt. Okay, so yeah, next one we still want to take a look at how to implement this, because this could be a very useful time-saving utility. So we'll just continue learning how to use it. Alright, so we have our proper controls there, which are the type, library, execute, and write control. So there are a few more entries we need to do. One is the HTC model entry, which we'll want to talk about. So yeah, let's take a look. So we want to use fixed reference temperature. Okay, so HTC model will be fixed reference temperature. Okay, so that's that, and we'll want the proper patch, and the patch we want to use, of course, is the oil to sphere patch. So we'll need a patches entry, and one will be called oil to sphere. Okay, and of course, if you specify a fixed reference temperature, you will need to give the what do you call that? You will need to give a reference temperature. And what is the syntax for that? Well, if we again, it's OpenFoam, what do you call that? The syntax or the documentation may be a little all over the place, a little hard to find, but thankfully we will have the reference temperature here. Okay, we have the syntax here. Okay, and this is an example usage for the fixed reference temperature mode. Over here it says HTC model local. Do not type that in, you will get an error. So that there needs to be some correction to this documentation. But apparently you will need two extra things. One is called the field, which is using the temperature field. One is called tref. Okay, so tref is T capital T capital REF. Alright. So remember that, I think according to the C++ code, that might refer to the fluid temperature we are talking about. Okay, so this is 300, and remember Kelvin. Always in Kelvin for OpenFoam. We always put our temperature in Kelvin, and the field will be T. So let's just put the entry there, field T. Doesn't matter the kind of doesn't matter what kind of the order in which you put all these, because remember in C++, as long as you declare the variables, you should be okay. All right, so as long as you declare all those variables in that little function box there. So let's do a little test run and see if this thing works correctly. We'll do an orange serial end. So it's going to run our usual utilities, going to split the mesh regions. So it's going to run chtMultiRegionFoam. Now again, if you want to check whether this thing is working correctly, let's take a look at the log chtMultiRegionFoam. Okay, and alright, so normally we take a look here. We have an error. Okay, so wall heat flux processing, yes, it's working well. But then it gives a warning, a request for object registry region 0 from object registry hot sphere in oil field. So you need to, what it's saying is that you need to specify the region. Okay, so we'll need to put in a region entry in there. If not, it will not calculate properly. So you have to resolve all these errors as they come up. Okay, so these are the errors of I think in there. So if they ask for the region, because they ask for the default region is region 0, but there are two regions already, so we need to put in the sphere and the oil or the oil. So we need to specify the region. So let's specify the region first. System control dictionary, and then we'll put the region here, region, and we'll put oil, and we just save and quit, all clean, all run serial, and I'll put an end there. Okay, so hopefully this time this thing will work a little better. Okay, so looks like okay. Usually we have this parafoam touch all for post processing, meaning the thing has ended. So it looks like chtMultiRegionFoam has some problems. Okay, let's take a look at the log. Okay, so the log says foam fatal error, incorrect first token. We expect an integer blah 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 found on the word oil to sphere. So alright, what does it mean? Means that probably looks like we need to change the way we write this we write this file. Okay, so we need to change the patch, the way we name the patch. So let's take a look at how we are supposed to name the patch. All right. So what we can usually do, I think, either you add some parentheses or you add this open inverted and close inverted commas. It should be able to work. All right. So we have already run all the snappy hex mesh and everything, so we just run chtMultiRegionFoam. Okay, so since we already done our meshing tools and splitting all the regions, we try and run chtMultiRegionFoam to just do a quick test, see whether this thing is working. Now still we have a fatal error. So coming back to this, probably the next thing we need to check is the brackets. Take a look at how the library is named here, library field function objects.so. So we can try putting in that syntax and see whether this thing works. Okay, so I'll put oil to sphere there, and let's do chtMultiRegionFoam. And okay, I'll put a Control-C to stop, and it looks like everything is working correctly. So I don't see any errors over here. Okay, looks okay. The chtMultiRegionFoam output. Okay, so since this is okay, what I want to do is just to do all clean, and then I'll do an all run serial n to do it properly. Okay, should be almost done with this thing. So it should be giving us data now. And normally we want to take a look at the post-processing. Okay, so we would expect that we want ideally to have a heat transfer coefficient file here, so that we can see the average heat transfer coefficient. Unfortunately, for us, this utility actually calculates the very local heat transfer coefficients of each little cell that I was talking about. Remember, we have to discretize this whole surface and the liquid into small little boxes. So what you'll do is calculate those heat transfer coefficients for these little surfaces, right? Okay, so where will the data be stored? If you take a look at one of them, you take a look at oil, we will have a new file here. See, heat transfer coefficient, we can go and do a VI into that. Heat transfer coefficient, and you see all of that there, all the data fields there. And take a look, see, we have a negative heat transfer coefficient, all of this. So we have all the little heat transfer coefficient there. Is it supposed to be negative? That's the thing. Okay, is it supposed to be negative? The thing is that, remember, what's the definition of heat transfer coefficient? We have the heat flux. Okay, heat transfer coefficient is heat flux divided by T2 minus T1. So T2 being the temperature of the surrounding fluid, T1 being the temperature of the solid surface. So the T2 interface with the T1, okay, or T solid, okay, And what is going on here? We have the heat flowing from the solid to the fluid. So the heat transfer coefficient equals to Q over T2 minus Ts. This is the fluid temperature. So okay, so T2 is greater than Ts. So T2 is about 300. Okay, then the solid surface is about 490 something. So what we can conclude is that the heat flux being calculated across the wall boundaries, that is an absolute value kind of a thing. It's not going to care about the direction. So H will be depending on this. So what it's saying is that the heat flow is from the solid to the fluid, which is definitely what we want. So if you take a look at the wall heat flux field file, again we'll see all of this, but we'll see that the heat flow is positive. So that's not very telling of where the direction is, the directionality is. So we have to rely on the temperature to tell us, okay, where's the heat flowing? If it's flowing from the fluid to the wall, then it looks as if this will be a good thing. I mean, it will be positive heat transfer coefficient. Of course, we can actually test this by changing maybe the fluid temperature to 500, the sphere temperature to 300, to see how these actually change. Okay. So yeah, I can just do a very quick run of that. So yeah, we can do a very quick run of that. So I'm back at the main folder. Okay. And let's say we want our oil temperature now to be 600 degrees C, 600 Kelvin. So what we can do, let's go to our system file. All right, and then we have all these older folders there we don't need anymore. Bottom air. Okay, I'll just get rid of this since we are at it. Right solid, left solid, top air. None of these are relevant anymore. What is relevant is the oil. So let's say we want, for example, the oil temperature to be about 600 Kelvin. Okay, so that should give us a little bit of change in the direction of heat flow. So in the change dictionary.dict, I can take a look at the T. I can change from 300 to 600. So the heat should flow in the opposite direction. So we can take a look at what the values of the wall heat flux and the temperature coefficient is. So we can see whether the wall heat flux values actually give us directionality. Okay, all clean. I'll run serial N. So it should be able to run. Okay, let's go and take a look at the oil, and we should have a wall heat flux here. So you can see the the values are now all negative, which means that the fluid is flowing from the oil to the fluid. Okay, and we can also take a look at the heat transfer coefficient, and now all the heat transfer coefficient is kind of positive. So okay, looks like the directionality is kind of opposite. Okay, when it's positive here, it looks as if the heat is flowing from the sphere to the oil, and then if you look at the wall heat flux utility, it is kind of inverted. So yeah, probably some directionality thing you need to be aware of. Okay, just be aware which value is bigger and smaller. Okay, and I mean use some common sense here to see where the heat is flowing from. You always flow from high temperature to low temperature. So but this should give you an idea of the sign convention when these functions are being used. So okay, I'm just going to see the oil. I'm going to change the dictionary back to the original 300 Kelvin. Okay. Okay, and I'm going to go back. I'm going to all clean, and now I'm just going to push these changes to Git. Okay, this is, oh sorry, that should be a git commit. Okay, so we'll just do a heat transfer utility adding. Okay, so thanks for watching. In the next video, I want to talk about a tool used to generate average values from the said heat flux field values, because we saw heat flux, we saw all these local values, we want to average it. There is a tool for that, and I want to introduce that in the next video. Thanks for watching. See you again.